Hello and welcome to yet another video in the series about the Pipeline Pilot Chemistry SDK, PPChem SDK. This example is going to be more ambitious, and we're really going to start manipulating chemistry here. Manipulating chemistry, of course, has a long history in BIOVIA tools. This started life as a Cheshire script and then was migrated to Pipeline Pilot. But now we're going to show you that you can use it in Jupyter Notebook. So let's get going. How do we start? The first thing we do is we import the chemistry SDK package, but I'm also going to import some other graphics methods and so on for displaying structures. So let's grab a molecule. We do it using this construct. So we use the mol.io class in the SDK, create an empty molecule object, provide a smile string, and then call the read molecule method. What does it look like? Well, then we use the matplotlib and so on and wrap it with a utility method that calculates a picture of the molecule, and then we simply pass in the structure. So if you're a chemist, this is a little bit horrifying, but that's what we're going to fix using our Fixmol capability. But the first thing we need to do is find the bad bits of the molecule, which are the nitro groups here. And we're going to do that using a smart string. We can put that into what we call our query molecule. And it's very similar to the target molecule code. So define an empty molecule, provide the smart string, and then call it. And we can also plot the structure there. And you can see we're going to look for those bad nitro groups. Okay, so how do we map the query onto the target? Well, that uses this SGMap module, one of the key modules in the SDK. It's very simple to use. We simply create a mapper object and then pass it to querying target and then just start calling it. So here I've asked to just print out the mappings. And I see I get these 4 lists of integers. And you would guess that these are the atom indices in the target molecule, and you would not be wrong. How can we show that? Well, let me rewind the mapping, and then what I'm going to do is change my display style. I'm going to do some highlighting and then put on the atom labels. So I can calculate the picture now with the highlighting and atom labels, and there you see the indices, 8, 9, 10, 11. And we can also understand why there are 4 mappers. So it's because each mapping hits twice against this because of a symmetry and hits twice against this because of a symmetry. But really what we want is once we fix this, we don't need to go back to it. So we only want the mappings that do not overlap. So that's really easily done by comparing the lists of indices. There's a utility function for that. And now I'm going to test it. So the first and second overlap mappings overlap. Yes, they do. But the first and third mappings do not overlap. Okay, so we got a lot of infrastructure in place. Now, how do we go ahead and fix things? Well, you need to take a step back and say the best way to do this is to define a class. And the class would allow us to define a query, do a mapping, find the mappings onto the target molecule, find the non-overlapping mappings, and then for each mapping, do some processing. In other words, say maybe change the bonds, change the charges, delete atoms and bonds, and that sort of thing to fix the molecule. And we would do this by subclassing this class for each type of fix that we wanted to apply. So it doesn't take a lot of work to do that. Here is a Fixmol mapper class. I'm not going to go through the code in too much detail, but you can see these methods, process mappings. This goes through all of the mappings, and then we'll see this init mapping and so on and so forth as well in action back in our notebook. So we grab hold of that module by just importing it, and we import the class, and now let's start to use it. So we want to subclass that class This subclass, nitrosep charge, is going to look for those particular functional groups there, the ones that we had there. Uh, Once it gets them, it finds them, it's going to change the bond order of one of the bonds to a single and actually fix the charges. So to find that subclass, we instantiate the subclass by giving it the smarts query that finds those kinds of substructures. And then all we do is we call process mappings on the target molecule, and it tells us how many bad functional groups it's found, and then we can actually look at what it did to the target molecule. And there we go, it fixed those two there. It didn't fix that one, of course, because it didn't match the target query, but another different subclass is easily defined, very similar in structure. Here we don't need to change the bond order, but we need to meddle with the charges if the charges are wrong. So it's easily done. Instantiate it, process the mappings. There was one bad group, and now we fixed it. Okay, so in the kind of legacy code, there's probably about 12 different badly drawn groups that it fixes. We're just going to step through a few here. So sulfones are next. So there's a horribly drawn sulfone. That group is not acceptable. And here is the subclass that's going to fix it. You can see we need to fix the charges and we need to fix the bonds. That's the query that's going to find that. There was one bad group, and now we've fixed that. Okay, so in everything we've done so far, we actually haven't had to delete atoms and bonds. We've simply changed them. When you delete atoms and bonds, you need to spend a little bit more time in your subclass because really the best thing to do is just create a big list while you're processing things, and then at the end delete the atoms and bonds in the list. So in this example, we'll see how that works. We've got a bunch of ionic bonds that are represented as covalent, so we want to delete these bonds. And in this class definition, we can see what we do is in the process mapping, all we do is we add the bond that we want to delete to this list that we initialize here. And then in the end mapping thing, we just delete all of those bonds. So instantiate it, process it. There were 3, and now plot the structure. So that more complex kind of behavior can be done as well. Perhaps a nicest example of this is in ferrocenes. So we have a rather long smarts query. It's going to have 11 structures or 11 atoms in it. The key thing to note here is in the process mapping, when we're trying to add the haptic bonds, then we're going to have this huge list of 11 atom indices, and we need to break that up into the carbons and then the metal. And that's what this syntax does. The Python slice command here is your friend. So this is going to carve out of that an array or a list of the carbons and then the metal. So we do that. There's the smarts query. There is the molecule as it was kind of originally drawn in the literature, but now we do this and we can have a more accurate representation. So in everything to date, we've kind of just focused on structures that had a single bad thing, but there could be more than one bad group in a structure. How do we handle that? Well, here's an absolutely horrible molecule, which is just for demonstration purposes. And it's very simple. All we do is we create a list of all the different subclasses that we need, and we just step through them in Python syntax, and we're done. So in this video, we've been a little bit more ambitious. We're now really doing chemistry in Jupyter Notebooks. It's perfectly acceptable to do chemistry in Jupyter Notebooks now with the ppchem SDK. We've read in molecules, we've shown how to display them, we've mapped a query onto a target, we found out whether mappings overlapped, and we've been able to process those mappings by subclassing a Fixmol mapper class, and works very well. So thanks for your time on this. It's taken a little bit longer than the easier videos, but I think it's very important capabilities. Look out for future videos about the Pipeline Pilot Chemistry SDK.